Alright guys, this is going to be our last little segment of the energy unit. It's been a big unit. We've sort of divided it into three parts, and I want to start the third part right now. So this whole unit, the subject has been mechanical energy. And we defined mechanical energy, just this isn't really a very technical definition, but it's a good working definition. And this is the energy associated with moving masses. And I had mentioned at the very, very beginning that there are two sort of parts of this, of mechanical energy, two different sort of forms of mechanical energy. And the first one we've talked about in great detail. That's kinetic energy. And kinetic energy we talked about quite a bit. It's literally this definition. It's the energy associated with an object that has mass and is moving, right? That was our equation. We said kinetic energy, K equals 1/2 the mass times the velocity squared. That was our kinetic energy equation. But I'd mentioned that there's another another form of energy, and that is potential energy. So it's possible for an object not to be moving, in other words, to have no kinetic energy, but still have mechanical energy. And that's a case where the object isn't moving, but it has the potential or the ability to move. So this, in some senses, I like to think of it as stored energy. An object having energy because it has the potential to move. So we're going to break this down into two different parts. We're going to talk about two different types of potential energy. But to give you a sense, before we even go into the math, let's imagine I've got the ground here. Here's the ground. And I've got some sort of a block, and the block is on the ground. Right? Here's this block, and it's on the ground. This block is not moving, and really it doesn't have the potential to move in the sense that it's not, unless something comes over and kicks it or something, it's not going to spontaneously start moving. So in this sense, we would say that it has no potential energy. But if I were to take this block and lift it up, if the block were instead up here, and I hold it there, it now has the potential, hold on a second, it now has the potential to move, right? If I'm holding the block here, gravity is pulling it down and it's off the ground, and so it has the potential, right? There's this force of gravity. So it has the potential to move. If I let it go, it will fall down. And that's one example. We'll discuss this in greater detail later, but this is one example of an object having the potential to move. It has energy stored up within it. Now, potential energy is abbreviated with the letter U. Sometimes you'll see me abbreviated PE as well, potential energy, but U is sort of the agreed upon abbreviation. And the units for potential energy, like all energy, the unit is the joule, just like we had for kinetic energy. Okay, so let's see how we could calculate the energy associated with an object, and we're going to discuss two different types of potential energy, and the first is the type associated with this block being lifted off the ground, and that's what's called gravitational potential energy. So let's break this down, two different types of potential energy. So we're going to start off with gravitational potential energy, which is abbreviated GU for gravitational potential energy. Actually, I'm going to abbreviate UG, U gravity. And in general, maybe I should have made this point up here. Let me make this point up here. In general, the potential energy an object has, in general, is the potential energy the object has is equal to the work done on the object, giving it that potential energy. So this is the general definition. The potential energy is equal to the work done. And that might seem like a weird definition, but I think if we do an example with gravitational potential energy, it'll make sense. So the gravitational potential energy, if I think about the work done, that's, again, to get back to this example of maybe we have this block on the ground. And let's say the mass of the block is, I don't know, let's say it's 5 kilograms. And what if I lift it 2 meters in the air? So I lift it up 2 meters. So I bring it 2 meters high. And it has a mass of 5 kilograms. Well, what work did I do in lifting that? Well, the work that I did to lift this, so the work that I did, so work done by me, is equal to the force I had to exert, which is the weight of this, mg, times the height that I lifted it, times the distance I lifted it, which is the height. So mg is 5 times 9.8, that's 49. The height is 2, so this would be 98 joules. So that means that when I lift it up here, the potential energy up here is 98 joules. So U here equals 98 joules. Now, one word on this before I continue. When I say that this has 98 joules, I'm implying that this is 0 joules, right, at the bottom. So I can say this is 0, or I can say that, and I can say that that's 98. In other words, I've defined the ground as my 0 point. And as it turns out that it's your free choice in these problems to set the 0 point wherever you want. So, for instance, some issues here. You could have called this your 0 point, right? This could have been your 0 point up here, in which case this would have been negative 98 joules. So you could have done that, and it doesn't really matter, because either way, when the block goes down, the kinetic energy decreases by 98 joules. It either goes from 98 to 0, or it goes from 0 to negative 98. Either way, the change, it goes down 98 joules. So in either case, no matter what, the change in potential energy is 98 joules, or negative 98, right? It goes down 98 joules. Usually in problems, what you'll do is you'll call the bottom point the 0 point. That usually makes the most sense. At any rate, back to this math. So before we said that the potential energy is equal to the work done, and right here I can see the work when I'm talking about gravitational potential energy is equal to the force of gravity times the height. In other words, this is equal to mg, the force of gravity, times height h. So that is our formula for gravitational potential energy. Well, I mentioned that there was going to be another type of potential energy, and that is elastic potential energy. So there's another way in which you can have potential energy, and that's due to some sort of a springy or elastic material. So, an example might be like a slingshot, right? If I had this slingshot right here. If I pull this slingshot back, right, and I put some sort of a rock in here or something. If I pull this slingshot back some distance, there's energy stored up in this spring. So this is some sort of this is a slingshot. And this is some sort of an elastic band right here. This is an elastic band. And I have maybe some sort of like a stone in here. And I pull it back, and the elastic band stretches and stretches and stretches. And when I pull it back and I stretch it back, energy gets stored up in the stone. The stone gains elastic potential energy, right? It now has potential energy. Because if I let go, the elastic is going to push the stone forward. So that's what we call elastic potential energy. And once again, we're going to say that the potential energy, so U elastic, it's going to be equal to the work done. So the work done, in general, is force times distance. But before we continue, we've got to rewrite this, because how do I'd like to have some expression for force that I can calculate. Well, what's the force in the elastic band or in any sort of elastic material? We need to address that before we can finish off this equation, so I'm going to do that right now. So elastic forces. And to think about elastic forces, I'm going to actually think about a different example. We'll come back to maybe our slingshot in a minute here, but I'm going to imagine that I've got I've got the ground here, and I've got this spring, and on the end of the spring I have a weight, some sort of a mass. So here's the ground, and there's this mass on a spring. And I'm going to say that this position right here, this is the relaxed position of the spring. This is the relaxed, or what's sometimes called the equilibrium position. So the relaxed length, which is sometimes called equilibrium. And then I'm going to imagine taking this and pulling the mass out, so stretching the spring. So the spring is getting stretched, and now the mass has been moved, and the mass is now over here. So here's the new position of the mass as the spring here has been stretched out to this point. In other words, I've stretched the spring through a distance, x. And what's going to happen? Well, hopefully it's obvious that if you stretch the spring out this way, that the spring is going to pull back in this direction, right? There's going to be a force backwards. I pull the spring to the right, the spring pulls back to the left. So this is the force here. And we'd like to know, what is that spring force? How do you calculate that spring force? The spring force, by the way, this equation I'm going to give you for the force on a spring works for any elastic material. It works for a rubber band, anything. Well, there's only two things that the spring force depends on, and I think one of them is obvious. One thing is how far you stretch the spring, right? If you stretch the spring a little bit, the spring only pulls back a little bit. If you stretch the spring a lot, it's going to pull back with a much bigger force. So it definitely depends on how far you stretch it. In other words, what I'm calling x. The other thing that it depends upon is how strong the spring is, right? Some springs stretch with very little force. You apply a little force and they stretch a lot, and other springs require a really, really big force to stretch them. Like an example would be like the springs in the suspension of a car, right? The car has a suspension. It can bounce up and down. And those springs are really, really strong, right? If even if you apply huge forces, they only stretch a little bit, like an inch or so. So the other thing that you've got to take into consideration here is what's called the spring constant, K, which is a measurement of the strength of the spring. So this is the spring constant. And the spring constant is measured in newtons per meter, which means if the K value were 1, that would mean if you applied 1 newton of force, it would stretch 1 meter. That would be a very weak spring, right? That's 1 newton is not a lot of force, and 1 meter would be a big distance to have this string stretch. So spring constants can be substantially bigger. They can be, thousands or even millions of newtons per meter. And then this is the distance stretched, of course. Usually we put a little negative here in front. That negative just indicates that if I pull it to the right, the force acts to the left. So in other words, the direction of X and F are opposite. That's all that means. So here's my spring force, my equation for the spring force. Negative Kx, that's all there is to it. So let's get back to our definition of elastic potential energy. Well, my force is given by Kx, so I'd like to plug that in for F. But maybe you can see right away, I don't know how obvious this is, but we're going to have a problem if we put Kx in here, because I'm going to take Kx and multiply it by d. What is d? Well, d is x. The problem is that as I stretch this spring farther and farther and farther, the force changes. In other words, the force is not going to be a constant value Kx, because as I stretch it farther and farther and farther, the force gets bigger and bigger and bigger. In other words, this force spring force here in this problem, this is no longer a constant. Not constant. And there's a way of dealing with this that involves calculus that I'm not going to go into right now. I'm going to give you sort of the kind of the punchline. I'm going to sort of tell you what the equation is, and the explanation involves calculus. There is one way of thinking about it that doesn't really involve calculus, and that's to say that really what I'd like to put in here for force, what I'd like to put in for force is the average force, right? I'd like this to be the average force. And the average force, hold on, the average force is going to be 0 plus kx, this is the maximum value, right, divided by 2. In other words, it would equal this, 1/2 kx. That would be my average force. And then I have to multiply by x again, because d is the distance stretched to x. In other words, if you didn't understand that, that's fine. Our equation is the elastic potential energy an object has is equal to 1/2 the spring constant k times x squared. So that is the equation for elastic potential energy. So two examples of potential energy, gravitational and elastic. In both cases, we imagine that you have an object with stored energy, or energy that's sort of stored up in the sense that the object having the potential to move, right? In the case if I lift an object off the ground, gravity gives it the potential to fall. In the case of, say, a slingshot, the farther when I pull the slingshot back, the elastic band, the elasticity of the elastic band gives the stone or whatever the potential to move. In both cases, the potential energy is equal to the work you do bringing the object to that position. In the case of gravity, that work is mgh. In the case of the elastic force, it's 1/2 kx squared. Okay, that's all for now. We'll practice this next class.